Okay, anyway, first going to give a brief overview of our parallel implementation, and then I'm going to talk about the mesh refinement algorithm we have implemented, the load balancing technique we are currently using, and since the parallel talk, we probably have to give some speed up results. Okay, so the strategy when we started this work in 2007 was to never store the entire problem in one processor, to minimize the memory usage. Use MPI because then it will be scalable. We can use different architectures. So to never store the entire problem in one processor, we implemented a distributed mesh. So we have smaller independent meshes on all the processors. And to make everything work together, we introduced ghosted data for all the shared entities. And we implemented some parallel pre- and post-processing routines. And since I'm a PhD student at U1, I had to implement some adaptive mesh refinement as well. Okay, so this was implemented in my master thesis with an old version of Dolphin. I think it was 07 or something. So now I've been working for 1 year, and I have cleaned up the code, so it's more general. So instead of using ugly hacks, I do the local to global mapping with the DOF map. Now it works for higher order elements. It should work for any order, I'm not sure. Now we have a full duality-based adaptive flow solver. And we have started to work, and it's almost done with implementing this new Rivara longest edge refinement. Okay, so what's the problem with mesh refinement in parallel? First of all, you have to make sure that you don't get these ugly hanging nodes on the boundary between the processors. Then, in order to assemble the matrix correctly, you have to make sure that you get a unique global numbering of all these new entities. The new entities which you add on this shared boundary. And then, if you add an entity on a shared boundary on one processor, you have to make sure that you propagate it to all the adjacent processors. And finally, it's nice if you can detect that the algorithm has terminated. Okay, to solve this problem, you can easily divide the refinement in a local part where you use an ordinary serial refinement algorithm, which will leave hanging nodes on this boundary between processors. Then you have a propagation phase where you transfer the refinement. And the key issue here is to propagate it efficiently and to detect that all the processors are ready. So this is the old refinement method. Most of you probably remember it. You mark some cells for refinement. Oh, let's see if we can get this working. This one. In the middle. You mark some elements for refinement. You find the longest edges. And then you bisect all the elements in pairs or in groups in 3D. So what this means for the parallelization is that you will only get one propagation phase. So it's fairly simple to implement a parallel. But you have some problems though, that you have to make sure that all the processors select the same edge. So we solved that problem by introducing a voting scheme. So all the processors cast a vote for one of the longest edges, then you exchange all the votes, and then you select the edge with the most number of votes. Okay, it fails, it works, but in 3D you have to have a cleanup phase at the end, because you cannot solve the problem perfectly with the voting schemes, because then you need infinite amount of propagation phases. So it's easier to remove the hanging nodes at the end. Okay, so the new recursive Rivara, it's almost the same, but now one can have multiple propagation phases between the processors. So that's difficult, and that means that in theory you can have infinite amount of refinement or propagations. And now the refinement is complete when all the processors are idling, of course. But the problem here is that the process can change from refining and idling and then start refining again, and then idling for 10 propagations and then start to refine again. So usually people solve this problem with Dijkstra's algorithm, that you count messages. So you invoke the refinement of one processor with a message, and then the controlling process waits for all the other working processes to acknowledge that they have got this start to refine message. The problem with this is that you cannot use it on the blue gene, because then you basically have a line at the end that says, wait until I received an acknowledge from all the 1,000 of processors. So our idea here is to include the termination detection in the propagation phase, because you cannot get rid of that communication step. And the good thing is that we know that this algorithm actually have a guarantee to terminate, so it's no problem. And when it doesn't work, when I debug the code, I usually look at the old refinement and compare it to the new one, and then I see it's definitely worth the effort to parallelize the new one. Okay, so load balancing. So when we refine on one processor, we will of course get a load imbalance, because we are only adding elements on one of the processors. So to solve this problem, we have to implement a load balancer. And an naive way is to simply repartitioning everything with FEniCS and then redistribute the data. That's not efficient, because you cannot guarantee that the new partition number 1 corresponds to the data that was stored on the old processor number 1 or the old partition number 1. Another key point here is that we want to do the repartitioning before the refinement, because then we have to move less data, and the refinement will in theory becomes more efficient, because we have to bisect an even number of elements on all the processors. To do this, we need a fast way to determine if load balancing is needed before we actually have done any modification to the mesh. This can simply be done by doing weighting dual graph of the mesh. So we consider that each cell take 1 unit of work, and if we refine with the old refinement algorithm, we set all the marked elements for refinement and all the adjacent elements to have a weight of 2, because they will be bisected once. And then you simply start the load balancing if you are above some threshold that you simply select.
Do you know a priori in the Rivara algorithm how many new elements you're going to add?
Yes, I'm going to come to that now. That's the difficult part here. Okay. Because what they do here is that they use a dry run of the old refinement. And then it works fine, because I don't need to bisect any elements, because it only bisects the longest one. But in Rivara, in order to get that one to terminate, then you actually have to change the mesh. Otherwise you don't introduce these new longest edges that... Yeah.
Right, you get some propagation. And so
yes, that's the problem. And it's a good question, because I'm looking for some good results on this, but I haven't found anything. So what I do is that I have a cutoff that I only do this recursion twice. And I use something that's called the longest edge propagation path. So that you... I should have drawn a picture, but but you can look at reference. It's Rivara. But you simply, from the unmodified mesh, you follow the longest edges until the new longest edge is the same longest edge as the one you propagated in from. Then you have a path that will be all the elements that will be refined from that element. So that's simply how we do the load balancing now. Yes, and when you have this this weighted dual graph, then we want to repartition it. And to get around this problem with redistributing too many elements from the wrong processor, that means basically that you want to minimize the total volume of data or the maximum number of data moved from one processor. You can use diffusive schemes to smear it out, but then you're basically stuck with multi-level complicated codes, or you use FEniCS and it's not open and freely available. So the more interesting part here is to use intelligent remapping. So you try to, given the old partitions and the new partitions, you try to reassign the numbering so in such a way that it minimizes the data moment.